Okay, the last section of chapter 6 is the division property of exponents. So before I tell you the property, I'm going to write this out the long way to show you why the property works. So this is x to the fifth over x to the third, which means in the numerator I have x times x times x times x times x. In the denominator, I have x times x times x. I should be able to cancel some of these, so I could cancel 1, 2, 3 of them. And then I am left with x to the second as my answer. Okay, I'm now the second one here. X to the third over x to the fifth is very similar. I'm going to write it out so you can see what's left, and then we'll look at the rule. Okay, so in the numerator, I have x to the third. In the denominator, I have x to the fifth. Okay, I can still cancel some of these x's out. 1, 2, 3 of them out. So I'm left with x to the second in the denominator, and I'll put a 1 at the top. Okay, so some of you have already spotted the shortcut. The shortcut is I can subtract the exponents because if you have x to the fifth over x to the third, 3 of them cancel, and I'm left with 2. This case, also 3 of them canceled, and I was left with 2. But where are they left? They're left wherever there's a higher exponent. So since the x to the fifth had a higher exponent, there were more x's at the top. So the x to the seconds were left at the top. In this case, the higher exponent was at the bottom. So there were more x's at the bottom, which is why the x to the second was left at the bottom. If you respect the higher exponent, you don't have to worry about positives and negatives. Okay, so division property of exponents. If you have x to the m over x to the n, I subtract the exponents and keep the base the same. But we are going to be careful about where the base ends up on the top or the bottom. And this is to make our lives easier so we don't have to deal with negatives. Okay, so let's look at example A. Okay, example A, I'm going to look at one base at a time. I see that I have m to the 13th over m to the third. First, where do I have a higher exponent on the m? The higher exponent's at the top. So I'm going to keep the m at the top. If I do 13 minus 3, I end up with 10. And why did I subtract? Because the 3 of them are going to cancel, and I'm left with 10. Now I'm going to look at the ends. Okay, where are there more ends? Wherever there's a higher exponent, the higher exponent's at the bottom. Okay, I have 7 ends at the bottom. If 5 of them cancel out, I'm left with 2. This is my answer. Let's go to the next one. X to the third, y to the 11th over x to the 7th, y to the second. Okay, and I'm going to compare common bases first. So first, let me look at the x's. First, let me see, are there more at the top or bottom? More at the bottom because there's a higher exponent at the bottom. Okay, I have 7 at the bottom, 3 at the top, which means I'm canceling out 3. 7 minus 3 leaves me with 4 at the bottom. Okay, now let me check the y's. Y to the 11th over y to the second. The higher exponent's at the top, so I'm going to keep the y at the top. I have 11 at the top. I cancel out 2 from the bottom, and I'm left with 9. For example C, let's check the x's. More x's at the bottom because the exponent's higher at the bottom. There's x to the 7th at the bottom, x to the second at the top. So if I have 7 at the bottom and I cancel out 2, I subtract, I'm left with 5. For the y's, the higher exponent's at the bottom. I had 5 at the bottom. I subtract 4. I'm left with 1. Okay. And the 1 is actually optional. You could just leave it y or y to the 1. Because I have nothing in the numerator, I have to put a 1 there. Let's look at D. X to the 7th over x to the third. The higher exponent's at the numerator. Okay, and the numerator of 7, 7 minus 3 takes me to 4. For the y's, the higher exponent's in the numerator. I'm going to put a little 1 here to remind myself that's an imaginary 1. I have y to the 8th in the numerator. If I subtract the 1 or cancel the 1, I'm in with 7. There's nothing actually left in the bottom, so I don't really need the fraction. If you want to put it over 1, you can. I don't mind. Okay, let's see. Higher exponent at the bottom. So m to the 5th is at the bottom. I'm going to subtract 2, or I'm going to say I'm half 5. I cancel out 2. I'm left with 3. And then n over n divided by n is just 1. Or they cancel out, and I'm left with 1. Okay, f, I actually have less letters now. There's more at the top. I have x to the 7th at the top. If I cancel out 2, 7 minus 2, I'm left with 5. There's nothing at the bottom, so I don't need a denominator. If you would like to put it over 1, you can. That's fine with me. Okay, for g, p to the 6th over p to the 10th, the higher exponent is at the bottom. So I have p to the 10th at the bottom. If I cancel out 6 of the p's, I'm left with p to the 4th. And because the numerator is blank, I have to put a 1 there. Okay, let's look at this one. H, x to the 2nd over x to the 2nd. Well, those cancel. Y to the 3rd over y to the 3rd. Those cancel too. If everything cancels, you're left with 1. Just like imagine if you had 5 over 5. 5 divided by 5 is 1. So something divided by itself goes down to 1. This is also why x to the 0 is equal to 1. Because 2 minus 2 is 0, x to the 0. Okay. Okay, for I, I'm adding some coefficients. Okay, so first I have these numbers in the front. Those are normal numbers. They don't have exponents. There's nothing weird. So I'm just going to divide them like a normal division problem. Do keep in mind where the bigger number is. 12 is bigger and it's at the top, so my answer is going to go at the top. But 12 divided by 2 is 6. So I'm going to put a 6 at the top. If I check the m's, the higher exponent's at the top. 7 minus 3 is 4. And then if I check the n's, the higher exponent's at the bottom. 10 minus 5 is 5. The last 3 has coefficients again. Coefficients are normal numbers, so this is a normal division problem, 20 divided by 4. The 20 is bigger and it's at the top, so 5. Let me check the x's. X to the 11th over x to the 8th. More x's at the top. 11 minus 8 is 3. There's no denominator left. I don't care about denominators. I don't need them. But if you really love them, you can put a 1 at the bottom. Okay, let's look at k. K has a 7 at the top, but there's nothing else, so I'm just going to keep a 7 at the top. Okay, now I'm going to look at the x's. The higher exponent for the x is at the bottom. There are 5 at the bottom. If I subtract 2 or cancel 2, I'm left with 3. Okay, now L, I'm trying to trick you. I'm not trying to trick you, I'm trying to make you think. There's nothing I see that's going to cancel, but I have this third power, which means I'm going to write this out 3 times. Okay, now let me look at the numbers. I have 2 times 2 times 2. 2 times 2 is 4. 4 times 2 is 8. That's at the top. Let me go to my x's now. X to the 4th, x to the 4th, x to the 4th. But they're all at the top, so I'm going to add them up. 4 plus 4 plus 4 is 12. Okay, now on the bottom I see I have a base of a y. Okay, but they're all at the bottom, so I can add them up. 2 plus 2 plus 2 is 6. Now, is there anything else I can do? No, because the bases are different. There's no numbers to simplify. Done.